In problem number 22, in section 5.5, we are asked how many different outcomes of winner and runner-up are possible if there are 6 contestants in a pie eating contest. Now, we can do this problem using the multiplication principle using the last section, 5.4, and we could think of it this way. We've got 2 slots to fill. What we want is a winner and a runner-up. And for the winner, we could select any one of the 6 people, and the runner-up any one of the 5, giving us a total of 30 ways to make these arrangements. Or we could think of it this way. How many ways can we arrange 2 objects out of 6? So this is just a permutation of 6 objects, 2 at a time. And if we compute this with our formula, we will have 6 factorial, right? The total number of objects in the top, factorial, and in the bottom, the number that we're not going to use, 6 minus 4 factorial. So we'll have, let's get that here, we'll have 6 minus 2 factorial, which will give us 6 factorial over 4 factorial. And if we break down this 6 till we get to that 4, we're going to have 6 times 5 times 4, then all the way down to factorial, over 4 factorial. The 4 factorials cancel, and then you can see that we're left with 6 times 5, which is just what we had up here with the multiplication principle. So we're still going to end up with 30 ways to make those assignments. Now, in number 26, we're asked, in how many ways can 6 people line up at a single counter to order food at McDonald's? So again, we can do this 2 ways. Here's the 5.4 way. We can just do it with the multiplication principle. Here's our 6 people in line, 1, 2, 3, 4, 5, 6. And in the first position, we can put any one of the 6 people. And then in the second position, any one of 5, then 4, then 3, then 2, then 1. This becomes 6 factorial, which is 720. Or we can think of it this way. How many ways can we arrange permutation, right? Arrange, permutation, 6 people if we take all 6 at a time. So by our formula, we're going to have 6 factorial. Now that 6 factorial is this 6 right here. That's the total number of people that we have, divided by this number minus this number. So we're going to have 6 minus 6 factorial. This becomes 6 factorial over 0 factorial. And what we need to realize here is that 0 factorial is a 1. So we are now going to have 6 factorial over 1, which is 6 factorial, which of course is just what we got up here using the multiplication principle. So either way, we're going to end up with 720 ways to arrange those 6 people in a line. In problem number 32, we are asked, in how many different ways can the 9 members of the Supreme Court reach a 6-3 decision? In problem number 32, we are asking, how many different ways can the 9 members of the Supreme Court reach a 6-3 decision? Now, to reach a 6-3 decision, we could have 6 justices, 4 and 3 against, or 6 against and 3 for. It really doesn't matter. We just need to get 6 out of the 9 or 3 out of the 9. And order doesn't matter here because we just want the decision. So why don't we compute the number of combinations of 9 justices taken 6 at a time? So we have a formula for combinations. Combination of n choose r we can write as n factorial, right? The total number of objects, factorial, that goes on top. And in the denominator, we're going to put the number that we're going to use, r factorial, times the number that we're not going to use, n minus r factorial. And in our case, we're going to be computing combination of 9 choose 6. So we are going to have 9 factorial, right, the total number of justices, factorial in the top, and in the bottom we'll put the number that we're going to use, 6 factorial, times the number that we're not going to use. Now look, if we're using 6, we're not going to be using 3, and that 3 comes from here, 9 minus 6 factorial. So this is going to give us 9 factorial over 6 factorial times 3 factorial. And that 9 factorial we can write as 9 times 8 times 7 times, and then we've got a match at the bottom. So we'll write the 6 factorial over 6 factorial times 3 factorial. But the 6 factorials, these are going to cancel, leaving us with 9 times 8 times 7 all over 3 factorial is a 6. And when I computed this, I got this to be 32. In problem 34, we are asked to work exactly 5 problems from an 8-problem exam. So the way I'm looking at this is that we've got 8 items, n is equal to 8, and we want to choose any 5 of them. And order doesn't matter, we just want 5 problems out of those 8. So it looks like we're going to be computing the number of combinations of 8, choose 5. This is going to give us 8 factorial over 5 factorial, the number that we're going to choose. 8 minus 5, the number that we're not going to choose, factorial. This is going to give us 8 factorial over 5 factorial times 3 factorial. And then the 8 factorial up here on top, we can break this down until we get to that 5 factorial in the bottom. So we're going to get 8, 7, 6, 5 factorial over that 5 factorial times 3 factorial. And then the 5 factorials, these are going to cancel. And now we are left with 8 times 7 times 6 all over 3 factorial, which is 6. And you can see now that 6's are going to cancel. And we are left with 8 times 7, 56.